it has been believed that quantum computing can be very powerful. Theoretically, people have proved that in many settings or problems, people have proved that quantum can be much more powerful than classical. Recently, people even successfully built some very interesting quantum computers to demonstrate that this potential is real. Honestly, these quantum computers are still very small, but it's already achieved the so-called quantum supremacy, which means that in a specific task of information processing task, these small quantum computers are already much more powerful than any supercomputer money can buy. So this is very encouraging. Here is the two famous examples. The left one is Google's superconducting quantum computer. The right one is Zhaohui Wei's optical quantum computer. But despite these encouraging progresses, quantum computing still faces a very, very serious problem. The problem is quantum noise. We can try to understand the situation as below. First, we know that quantum effects, in most cases, are based on very, very tiny quantum devices, which means that this kind of information is very fragile. It's very easy to destroy by any environment or noise. So, in some sense, we hope that these quantum devices that are used to do quantum computing should be as isolated as possible. We have to isolate these quantum devices with the environment to avoid quantum noise. But on the other hand, because it's a computer, you have to control the information freely, which means that you have to build some collections with your controlling device and the computing device. So, which means that the quantum devices that records quantum information cannot be isolated. But we need both here. We need both. So it's a contradiction. That is why quantum computing is so hard to build. People believe that the ultimate approach to fight against quantum noise is error correcting. You have to introduce redundancy and encode one small piece of information into a larger one, much larger one. Because usually the quantum noise is local. As long as you have a lot of sufficient redundancy, local noise cannot destroy the whole information. This is the basic idea of error correcting code. But the bad news is that people have convinced almost everyone that this is promising. But the bad news is that this approach is really, really costly. The cost is so high that it is way beyond our reach for now. We believe for the next 10 or 5 or 10 years to come. People believe that 10 years later, maybe we can handle this approach. Okay, as a result, the quantum computer we just mentioned a moment ago have no error correcting. For now, a central topic in quantum computing is how to reliably implement quantum schemes, quantum algorithms using untrusted or unreliable quantum devices. This is the central topic in quantum computing. In this talk, we will focus on a very specific task of this sort. We can imagine that in quantum labs, if you want to demonstrate that you have developed a very, very promising approach to build a large-scale quantum computer, the first step, you have to convince us that you can successfully prepare a very large entangled quantum state. For that, you have to find an efficient approach to certify, to convince us that you do build such a quantum state. So certify unknown quantum states because we means everyone except the experimentalists do not believe that you can do that. So you have to certify that for us. But the point is that if you want to certify that you do prepare such a state, you have to convince that you have to prove that the state that you prepare is has a certain density matrix, because in physics we know that this is the information of the quantum system, right? And the problem here is that the size of density matrix usually is very, very large. For example, if you have 10 qubits, and the size of the density matrix will be the 2 to the 10 times 10 to 2 to the 10. It's really, really large. So what you can do is that we know that in quantum mechanics, if you want to certify an unknown quantum state, the only thing you can do is measure the states. But if you measure the states will be destroyed in a typical case. So you have to repeat the process over and over, collect the corresponding statistics. Besides, you have to choose a proper setting wisely to dig out as more information as possible. And after choosing the settings to measure, you have to repeat the experiments over and over, collect the statistics, and you convince us by some computing which use statistics to certify the target state. You prove that, okay, the state is indeed our target. This is a very, very common situation in modern quantum experimentalism for quantum computing. For example, in the 1 or 2 months ago, Professor Duan, I believe he's here right now. They built a very, very large untrapped quantum computer. There, I asked an insider of the group and how to certify the state. He convinced me that the best they can do is only dig out very, very tiny piece of information of the target state, because the information is so large in some sense. So okay, we can appreciate the situation here. For example, typically, if you want to certify an unknown state, if you a most common approach people are using is it's called a quantum state tomography, because the basic idea is very straightforward. Here is a density matrix. For any density matrix, you can express it as this formula. Here is Pauli matrix tensor products. Here is some coefficients. Here, the good thing is that this quantity you can measure somehow. So as long as you find out every coefficient here, in principle, you can rebuild the state. And based on that, you can certify the target states. But the problem is that here, the possibility of the setting you have to measure is really, really huge. Every position has 4 possibilities. So overall, you have to handle 2 to the 2n number of settings to measure. For each setting, you have to repeat the measurement over and over to collect the data with high enough precision. So we can imagine this is very, very challenging to handle if the size of the problem is a lot small. To my knowledge, okay, I believe this is true. The largest quantum states that people have tried this approach is only 10 qubits. It's only 10 qubits. So, but here we have to mention some further results on this approach. Here, the cost is corresponds to the situation you have no any information beforehand about the target. If you know something, you can do much better. For example, if you already know that the target state is a stabilizer state, or you have know that the density matrix as a matrix has a very low rank, the approach could be much easier. but still it's very costly. And people already developed a lot of other approach to handle similar tasks based on different approach. Okay, here is some well-known approach to certify quantum states, unknown quantum states. A common feature is that here we have to assume that the quantum device you are using is reliable. Otherwise, the approach will fail. The approach will fail. So this is exactly the reality for now. Because if you ask quantum experimentists on quantum computing, you will find out that for now, they have, usually they will mention 3 kinds of different quantum operations. Okay, single qubit rotation, 2 qubits entangled gate, and quantum measurement. The first 2 is relatively good for now. For example, even 2 qubit gates, they already realize the fidelity of 99% or even 99.9%. But as of quantum measurements, the quality is really, really low. For example, last month, okay, we will mention this again. Tencent used their superconducting quantum computer to demonstrate the theory we are introducing. And I observed that the quality of the measurements, okay, this is not Tencent's fault, it's our human's fault. It's only 93%. It's really, really low. So it's fair to say that we cannot put too much trust on the measurement devices. So theoretically, we can ask the following question: what if the measurement device are found unreliable? How we certify the state reliably? Okay, there are other stories. In other stories, for example, you buy some quantum device from a foreigner or even your enemy, and you conduct some security relevant quantum protocols. In that situation, you cannot trust the quantum device too much, right? So you have to find out a way how to certify. Okay, how to reliably conduct the target protocols based on this kind of device you don't really trust. In this situation, the approaches we just mentioned don't work anymore. So in such a situation, we ask how to certify the states with such an unreliable device. Okay, you can imagine. This sounds mission impossible. For example, you want to measure how long is this room, and you have only one ruler. The ruler is very, very terrible. Your friend tells me that the ruler is not accurate at all. It's very terrible. So you have to use this terrible ruler to measure how long this room is really challenging. But people have known that this is possible. This is possible. The first approach of this kind is the so-called quantum self-testing. Okay, to introduce, our approach, we are based on this somehow, but with different theoretical foundation. So before introducing our idea, we have to look into the working mechanism of this approach. We have to mention the so-called Wei experiment. We believe everyone is very familiar with this. It's a very important experimental test to verify whether quantum mechanics is correct. This is really, really huge. Okay, as a result, this kind of experiment confirms that in nature, there does exist the so-called nonlocality. It is involved in the Nobel Prize 2 years ago. Okay, the setting is like this. Suppose Alice and Bob are separated. They want to play the following game in a collaboration way. At the beginning, each of them have an input x and y. Each of them is a bit variable. And after receiving the input, they have to immediately output a corresponding bit, A and B. before the game begins, they have the chance to share some resource which can be quantum or classical, and in different setting we can repeat the experiment over and over and collect the distribution like this, which means when the input is X and Y, the distribution, the probability that Alice and Bob output A and B respectively. The key point is that when the game begins, they cannot communicate at all. Any correlation between the output only depends on the sharing resource beforehand. Okay, we believe everybody is very familiar with this. The result is that the people have confirmed that in quantum world, you can produce more correlation than in classical world. Strictly logic. This is really, really important. Why we mentioned this fact? Because this is about the foundation of quantum mechanics. Because recently people realize that instead of looking to the foundation of quantum mechanics, we can use this property to do a lot of things good for quantum computing. Okay. Before introducing this, why this is the case, we have to mention another notion, Bayer inequality, which is a how to say a tool to review the gap between the correlations that quantum can produce and the set of the correlations that classical can produce. We know that in classical world, every correlation has to satisfy the so-called Bayer inequalities, but the people have found out that in quantum world, this can be violated. This is the Nobel Prize thing. But a relevant fact on quantum computing here is that 10 years ago, Andrew Yao, okay, this is the Yao involved in this conference, and his students found out that if you look at the Bayer inequality, that's a very interesting thing. If you observe, if you confirm that a certain quantum system can violate this Bayer inequality maximally, which means you only need a quantity corresponding to the left set, and you can prove that this is the best you can do. If that is the case, you can pin down everything up to local assumptions. You can pin down everything, which means if you do such experiment, you observe the maximal violation. Even you are using the most terrible quantum devices you can imagine. As long as you observe the maximal violation, you can pin down the states. You can pin down the quantum measurements. This is really, really valuable for quantum computing because this provides you a very, very interesting approach to certify something reliably using unreliable quantum devices. Okay, the basic idea is that as long as you believe quantum mechanics is correct, the statement by Yao is correct. So it's mathematical proof. Recently, people using this very important fact to develop a lot of very interesting protocols. For example, this is the most, I believe, is the most convincing way to show that this idea is very valuable. Okay, you are doing some QKD thing. QKD means it's quantum key distribution. You can imagine it's very relevant to crypto. And you don't believe everything. You don't believe the device you are buying. You don't believe the channel you are using. But you can, based on this fact, to believe something. This is the key fact. Okay, recently people have conducted experiments to demo that this idea is theoretically valuable and experimentally durable experimentally. Okay, but the thing Andrew Yao and his student did is a very specific example. People are wondering whether we can generalize this fact to arbitrary case, which means can we develop a systematic way to certify any quantum states? Okay, if you are not familiar with this story, here the only state that Andrew Yao certified is is EPR states. It's a specific state, two cubic states, and that's why people ask whether we can do this for any quantum states. Okay, recently people have made very remarkable progress. For example, 7 years ago, people proved that bipartite means two-party. Bipartite pure states can be certified this way. And last year, very recently, people proved that all multipartite states can also do this way. On the other hand, we prove that any mixed state cannot do this way. The basic idea is very simple. If you generate some correlation with a mixed state, you can always find another pure state which has nothing to do with the mixed state. It can also produce that correlation, which means that as long as you observe the correlation, you cannot tell whether it's from a mixed state or mixed pure state. So that's why mixed states cannot be certified this way. Okay, another relevant fact here is that as we mentioned again and again, here for self-testing, the key concept is quantum nonlocality, which is crucial because the basic idea is that you have to make sure that as long as you observe such a correlation, you can prove this correlation can only come from certain quantum states, pure quantum states. That is the basic idea of self-testing. And which means that each party has to conduct at least two different setting environments. Why is that? Suppose we have such an experiment where each party conduct only one environment, then the correlation will look like this. Here, that's no x, y, because x and y is the label of the setting of the environments. Here, that's only one setting, so we don't have x and y anymore. We only have P, A, B. For such a correlation, it's very easy to prove that you can generate such a correlation quantumly. You can also do that classically, which means when you see such a correlation, you cannot tell which system it comes from. That's why we cannot certify anything with this kind of correlation. Okay, which means self-testing based on this kind of simple experiments is impossible. A very easy to understand example is like this. Suppose we have such a correlation. You can easily, in 1 second, just find out two candidates to generate such a correlation. This is the entangled state. Here is the classical state. As long as marry both in the computational basis, you can generate the same correlation, which means if you see this, you cannot tell whether it's come from here or here. So we cannot certify this. Why we consider such a ridiculous situation? Because the following. Because, okay, maybe you can see very soon in 2 minutes. Okay, in summary, we have known that self-testing is very valuable. It can certify quantum states reliably using unreliable devices. This is the key feature in quantum information processing tasks. For now, we do not have high-quality quantum devices. That's the key fact. But another fact is that non-locality is necessary for self-testing. But it's a bad news, a really bad news is that non-locality is extremely challenging to observe reliably. For example, several years ago, 9 years ago, there's a breakthrough. 3 groups at the same time reported the most convincing experiment to demonstrate that in nature there does exist non-locality. Okay, this story is very complicated. We don't have time to look into the details, but the key fact here is that quantum non-locality is extremely challenging to observe. So we ask the key question, can we design similar protocols without non-locality? Without non-locality. In the previous slide, we have convinced you that if you do the generation straightforward in a straightforward way, you will fail. You will fail. Okay. After discussing with experimentalists for many times, we ask the following question. We believe this is the key starting point. What if we know the quantum dimension? Why we ask such a question is that when you talk about quantum experimentalists, you will find that in most cases, the thing that they cannot do very well is the precision, the fidelity. For example, if you, and now we are collaborating with some optical group, very small quantum experiment, you will realize that the quantum fidelity will drop to 90% easily. So in this sense, precision is not so high. And but there's one thing, it's very obvious. In most cases, quantum experimentalists know very well how large is the quantum system, which means which degree of relevance in their experiments is really clear. So we believe that this question is a good question to ask. What if we know the quantum dimension? Besides that, we know nothing. We know nothing. Can we do a self-testing like protocol? And in this talk, we'll convince you that this is possible. Okay, half an hour. I think it's sufficient. We now prove that if quantum dimension is known, besides that, we don't believe measurements, we don't believe quantum gates, we don't believe the states you are using, we believe nothing except quantum dimension. Okay, which means if this is possible, our protocol, new protocol, will still enjoy the crucial property that you don't trust the devices, but you can certify the state reliably. So this is the key feature that we want. So it can bring us remarkable convenience in certifying quantum states. Last month, Dr. I mentioned, Tencent has confirmed that the following approach is doable. Okay, if you are interested, you can see such a paper. Okay, how we come up with this approach is based on a different story, which is not from physics, it's from computer science. Okay, so which means we have to tell another story to introduce how we came up with such a solution for this problem. Okay, we know that studying quantum advantage in computational power is a central topic in quantum computing if you are computer scientist. However, in the most general model, for example, Turing model, it's extremely hard to prove means we have to certify it's correct mathematically. This is hard. We can see such an example. For example, the Schwarz algorithm is a milestone, right? But rigorously, we still cannot rule out the possibility. Maybe 10 years later, some smart guy come up with a classical algorithm can do the same thing in polynomial time. We cannot rule out the possibility for now. So, which means here, the best we can do is such a statement. Okay, Schwarz algorithm can do this problem exponentially faster than any known classical algorithm. That is a standard statement on short algorithm. But still, there's a possible, though not very, it's not probably, it's possible that some classical algorithm can do the same thing. So here, the point is that in typical case, quantum advantage is very hard to prove. But somehow people have managed to achieve this in some specific model for computing. For example, in computer science, if you are interested in the query complexity, communication complexity, some AI system, people have proved that quantum is more powerful. It's more powerful. But it's not good enough. It's not good enough. Because in most cases, what people do is identify the advantage. How to measure the advantage is still a problem. So here, the lesson we learned is that, okay, here is the general model we can do. We can't do anything. Here is a specific model we can do much better. Here, the lesson we learned is that the simpler the model are, the more we can find out. So why not consider a simplest model? The correlation generation we just mentioned is the most simplest model we can imagine in the region of quantum information processing. So here, probably we can find out more. For example, here we cannot do anything on quantum advantage. Here we can identify the existence of quantum advantage. Here we want more. This is the case. It turns out we can indeed achieve something unimaginable in this simple, in this more complicated models. Okay, the model is like this. Suppose Alice and Bob, we just mentioned this setting. They just want to sample a correlation, which means that, okay, somehow Alice output A, Bob output B, according to such a distribution. This is the whole task. This is the whole task. It's so simple that everybody can know very easily, right? The amazing thing here is that as long as you focus on such a simple example, you can do whatever you want. You can do whatever you want. Here, okay, let's take it slow. Okay, because this is so simple, you can do this quantumly, you can also do this classically. Quantumly means that at the beginning, Alice and Bob share a quantum state. Then Alice locally measure his system. Bob locally measure his system and output the outcome, which is exactly the target. In the classical world, Alice and Bob can share a coin. For example, they can look at the weather, whether it's cloudy or rainy tomorrow. And tomorrow, when the truth is known, they can do the corresponding sub-protocol. In such a way, they can produce such a correlation. Here, what we compare is how large the shared resource has to be ready to prepare the target. For example, in quantum, we focus on the number of qubits of the initial shared states, such that you can achieve such a task. In the classical world, similarly, we focus on the number of the coins you have to share. We define the costs to be the size of the initial resource they have to share. And it turns out we can pin down every setting completely, which allow us to compare the power of quantum and classical in such a simple example, in such a simple task. Okay, I think here the relevant fact is only we can characterize the costs for both protocols completely. In classical world, the cost is exactly the logarithm of the so-called non-negative rank, which is very similar to the normal rank. We decompose a target P into a sum of a bunch of rank 1 matrices. We count the number of the rank 1 matrices we have to prepare to decompose the target P. Here is the number of the rank 1 terms. Similarly, okay, because the time is limited, so quantumly the cost can also be characterized completely by the so-called PSD rank. The cost is exactly the logarithm of the PSD rank of P. Okay, if you are interested, you can find out what is that in 5 minutes. So here we do not have time to look into the details. Anyway, key point is that for this simple task, you can characterize both at the same time. Okay, you can see such a paper is a long time ago. And which means we have a very, very good platform to compare the power of quantum classical. It turns out the gap could be huge, could be anything, could be exponential. And which means quantum enjoys a remarkable advantage on this problem. And this is the rare moments that quantum advantage can be quantified. Okay, based on this fact, we do a lot of interesting things. We believe it's impossible in other complicated settings. Why we mention this story so carefully? Because recently we consider a further question. Okay, recall that in the last slide, what we do is that, okay, we give you a P, we have to generate or sample such a P based on a quantum protocol. Okay, the old result tells us the minimal shared initial state you have to prepare to obtain such a correlation. Here, the key point is that we only know the minimal size of the seed. If somebody, your friend tells you that, okay, I have a specific state, its size larger than the minimal size. Can we do the same task with this specific quantum state? It's a very, very realistic problem. Okay, we found out this problem has very, very rich mathematical structure in the sense of information theory. And it turns out, as long as P has a certain property which is consistent with another property of the state, you can certify. You can answer the question of your friend whether it can or cannot. Okay, this is a very new result this year. So here the key point is that we have defined two properties for a correlation and a state. The correlation is well known. The property of the state is well known. It's called the Smith coefficients. It's well known. And we define a new concept, which is a property of the correlation. As long as the correlation has such a property consistent with Smith coefficients, we can confirm that that state can prepare such a. This is a very straightforward result. Okay, the technique is very boring. We don't have to go through the details. Okay, here is the key. Okay, inspired by the new result, very recently we asked the following question. Suppose you have a P. Whether it is possible that this P has only one corresponding quantum state which can generate such a P. If this is possible, which means in quantum lab, if we observe such a P, we can certify that the underlying state must be that state. This is the basic idea. But the story is, the basic idea is simple, but the mathematics is very, very complicated. Okay, it turns out, we find out for a typical P, usually in most cases, you will find a lot of pure states which share satisfying property consistent with the same P, which means if you observe such a P, there are more than one possibility you prepare such a P with the minimal size of quantum space, which means you can not certify anything with such a P. So our task is very obvious. Whether we can find a P in such a way that there's only one state consistent with such a P. We can go a step further. In quantum lab, if we want to certify that, if you are Professor Pan Wei, and you built a very large quantum computer, and an expert comes, and he wants to convince the expert that he successfully prepared a very large quantum states. So he has a target in his mind. He has a target. What he has to do is certify that the target is really, really what he wants. That is the key point. If that is the case, a possible way for him is that he can come up with a proper P in such a way that in this size, there's only one state consistent with such a P. This is the high-level idea. Okay, after several months, we found out all of this kind of, conjecture is correct. And again, there are a lot of details you have to take care. For example, you have to convince the expert that, okay, in the region of pure states, there's only one possibility consistent with the target P you are designing. In addition, you have to make sure that there's no any mixed state. Mixed state can produce the same P. Again, in the old story, what we can take care is only pure state. Okay, you have a P, you have pure state. How to certify that pure state is a target? You have to make sure that this P only consistent with such a pure state. In addition, there's no mixed state that can do the same thing. This is the most complicated step in our protocol. If this is the case, essentially we have self-testing, which Professor Pan can certify that the state is really what he wants. Here, the good thing is that there's no non-locality, which means the experiments is much easier to conduct. That is the truth, because we have confirmed this point in Tencent's superconducting quantum computing last month. Okay, this is the main result. It's very okay. We have 4 results. The first one is that, okay, suppose you are in your mind is a maximum entangled state. It's a maximum entangled state. Then you can come up with such a P, which is not unique. But this is sufficient. If you in quantum lab observe such a P, you can confirm that the underlying state must be entangled pure state. The main idea for the proof is the 4 steps. I think I already introduced the basic idea. First, you have to prove that there's only one pure state consistent with such a P. And the second step and the third step is that there's no mixed state that can generate such a P in the minimal size, which means the quantum dimension is already known. That is our assumption, remember. And As a result, the quantum state can be pinned down mathematically, which means as long as you believe quantum mechanics is correct, we have all these facts. And this can be generalized to arbitrary case, which means if in your mind it's an arbitrary quantum states, it's quantum states which with very ugly Schmidt coefficients, for example, you can design a equally ugly correlation in such a way that as long as you observe such a P, you can prove that the underlying state is your target. We can customize the P based on the target state in your mind. Okay, that's why we call this a certification. It's a certification. Okay, can we do better? Which means that can we use a more efficient correlation to certify the target? We have proved that suppose the target state is P times T, D, sorry, means that each subsystem, the dimension is D. And the best we can do is come up with a D plus 1 times D plus 1 correlation to certify this state. Why this is the case? Because if you go one step further to reduce the dimension of the correlation by single dimension, you will fail. You will fail, which means as long as the correlation is D times D, you can always find a classical state to generate the same correlation, which means the correlation cannot certify anything. So this is the best we can do. The first step is this is what Zhaohui asks us to do, is that we prove the very, very complicated robustness result, which means in quantum labs, even if you come up with a target P that qualifies to do amazing thing, but you have to make sure that if in quantum lab, the real correlation you observe is not P, but really close, can you do a similar thing? Okay, this is very, very important. If you cannot prove this, your protocol is only for fun. There's no any real value, right? So we confirm that this is the case. But the result is very weak. It's very weak. To find out the truth, we conduct very complicated numerical calculations, and it's based on non-convex optimization to confirm that this protocol has very, very strong robustness, which means that as long as you observe approximate correlation, you can certify that the state will be very close to the target in your mind. Okay, this is the key. This is the key information convinced the Tencent to conduct the experiment. Okay, the discussion. As we mentioned, if you want to certify a non-stabilized state in quantum lab, for now, it's really challenging. It's really challenging. The largest states that people have tracked QST, quantum state tomography, is only 10 qubits. We know that 10 qubits is really, really small. For now, we hope that the quantum computer could be hundreds qubits, hundreds. So this idea cannot be used in even a little bit larger system. So we really need a new theory to tell quantum experimentists how to certify states more efficiently, especially when currently the quantum devices you are using for measurements is really terrible. That's why we come up with such a project to find out new ways to do this. And okay, we already know that based on unreliable quantum device, you can use the self-testing approach to certify states. But we know that self-testing is really challenging to implement. So here we come up with a new way to do the self-testing like protocol. But the foundation is not nonlocality anymore. It's a new concept from something. people play with in the optimization theory and the computer information theory. It's different foundation. Here we have fewer measurement settings in the quantum lab. Okay, we have a lot of details to mention if we have 2 hours, for example. Okay, the first thing Tencent asked us is that, okay, we believe your theory is correct. Such a P is so ugly. How can we observe such a P in quantum lab? So we spent 1 month or 2 months to come up a very friendly P in such a way that you can only you only need to measure the states in poly observables. You can you can observe or qualify P. Later, our theory will prove that as long as you see an approximation of such a P, we can do very non-trivial results, which is the certification of the states. So this is really experiment friendly. I believe this is the best you can do. But for now, there are very serious problems to handle further. First thing is that the robustness is still an issue. We know that self-testing was proposed in 20 years ago. In the past 2 decades, people came up with a lot of theoretical approaches to analyze the robustness. So you can imagine such a situation is unavoided in our approach. We have to handle the robustness very, very carefully. For now, the result, the theoretical robustness result is really, really weak. It's really, really weak. So that's why this is really weak. That's why we use the most powerful computer available to us to this calculation spent 2 months to draw such a very promising figure to convince the analysts this theory is realistic. Which means there's a huge gap between the theory and the numerical. We need to find out a more smart way to prove the robustness, which is very important because you have to customize your robustness based on the equipments you are working with. For example, if you are working with optical quantum experiments, the robustness of the protocol will be different because their weakness is in different places. But if you are working with superconducting quantum experiments, their weakness is very obvious. The measurements, a detector is really, really terrible. So you have to customize the robustness. That's why we list this as the first open problem. And the second thing is, can we generalize the protocol to the multiple type case? Recall that for the original self-testing protocol, the bipartite case, general case is proved in 1917. And the multiple type case is only proved last year. So we can imagine this is highly non-trivial, but we really want to generalize our theory. But the difficulty is obvious. If we look into the details of the proof, we will see that we mentioned a key concept called TSDY. This concept is only for 2-dimensional. And for now, for the multiple case, there's no any non-trivial result on this concept. This concept plays a key role in this protocol. So if we want to generalize the bipartite case to the tripartite case, it's like in quantum mechanics or classical mechanics, the generation will be highly non-trivial. We don't have any idea for this. Okay, this is the talk. Thank you.
Knowledge of quantum computing very, very minimal. So maybe it's a very naive question.
It's okay.
So if I understood, the main idea is that you can show that if you observe certain correlation, you can deduce from it what was the underlying state that generated them.
Yes.
But in practice, are they frequent enough that you actually observe this correlation, or is it very rare to actually see them?
Okay, that is a very good question. Here we have a different layer of fact. The first thing is that in quantum lab, quantum information is what you cannot see. You can only feel that by measure the target state and collect the data, analyze the data, right? But in most cases, if you do that straightforward way, the cost will be incredibly high, like QST in profit. So we have to find out a much more efficient way to certify. Okay, experimentalists usually do such a thing. Okay, he does his best to prepare a state, but he has to convince the referee, he can convince the colleague that he really achieved that. So he has to certify that. In his mind, he knows that the target probably will be something. But if you want to convince somebody that this is the case, you have to find a clever way to design an experiment. Okay, as long as we see such a pattern, okay, we know there must be something here. And if you want to pin down everything, you have to come up with a very, very complicated correlation. We see all the details of the correlation for sure. Then we prove as long as quantum mechanics is correct, the state, the underlying state must be the target. This is the whole story. Okay. Thank you.
Question? Okay, if no, let's next speaker.
Thank you.